Alright, hello everybody. Today we're going to get started on homework 1 part B for process dynamics. And today we're going to look at a two tank system that are gravity drained. And we're going to be looking at this system with a proportional integral controller. And so what this proportional integral controller is going to show is we are going to have some integrals in our dynamical material balances. And then what we're going to be able to do is apply our fundamental theorem of calculus to eliminate these integrals and isolate the variable to show it as an intermediate state variable. All right, so we're going to get started first off by drawing our system here, where we have just a simple gravity drained two-tank system. So we have our tanks. And what we also need to look at is that all of these tanks have a certain liquid height. We're going to call these H1 and H2. And what we also want to see, and we're going to call these Qn, Q1, Q2. And what we also need to see is that these tanks all have drainage holes. And if I look at the problem, the cross-sectional areas of the tank, which I will identify with the big green circle here, call that cross-sectional area is 1 meter squared for this problem. And then the drainage holes, or we'll call these H equals 0.1 meters squared. And so like in the previous problem, we're going to start by applying our regular equations, where we have A dH1 dt equals, we set this to Qn, or Q1, I keep this as Qn, minus what we derived for what would be Q1 in this scenario, which is A out, we call it, square root 2g h to the 1/2. And we'll rewrite our second equation just to say dH2 over dt equals Q1 minus Q2. But in this instance, Q2 will be rewritten as A out square root 2g h2 the 1/2, and we'll call this out as h1. So now we're going to derive our dynamical material balances, and then we'll also apply our fundamental theorem of calculus to be able to isolate and simplify our balances. So once we have our two fundamental equations here, what we can then do is just begin writing our equation for our Qn, where we have our Q initial, which has the bar over top, and then we're going to add our controller gain times our error of our h set point minus h2. And so this portion on the right-hand side, this controller gain times our error, we encounter an issue which is called proportional offset. And this is caused because we have a proportional only controller. So how we can eliminate this issue is we can bring in something that is called a proportional, I'm going to abbreviate this, integral controller. And what this proportional integral controller allows us to use an integral which will eliminate or reduce and potentially eliminate our offset that we have in this equation. And so when we want to apply our integral controller, we can look at it as Ki, and then it's an integral controller, so we simply look at it as an integral from 0 to our value of t, or time in this scenario. And this will just be our same equation as our error, which is h set point minus h2. And now what we do is we actually integrate this in terms of tau. And so moving forward, when we see this integral, it becomes a major issue. So what we can do is we can actually apply the fundamental theorem of calculus to eliminate this and get our dynamical material balances. Next, what we're going to get into is we are going to simply reapply our equations seen up here. And we are simply going to rewrite them using now our new Qn value. And so what that's going to look like is dH1 over dt is equal to 1 over A now Qn plus our controller gain times our error plus our proportional integral controller t of hsp minus h2 d tau, and then we're going to end up subtracting q1. And so this is simply this equation up here. It is this top equation, just made or rewritten differently because now we are concluding a proportional integral controller. And so our second equation for now, we are just simply going to rewrite as dh2 dt equals 1 over a q1 minus q2. So now that we have these two equations set up, what we're going to get into next is we're going to use our fundamental theorem of calculus. Which really all the fundamental theorem of calculus shows us is that when we take the derivative of an integral, say for this instance we are doing the integral of our error because that's what's the integrand inside of our integral, or dt equals hsp minus h2. So we've shown what our fundamental theorem of calculus looks like. We're going to label this FTC for fundamental theorem of calculus. So now we can rewrite and reapply this into our equations to be able to simplify them and have a more effective dynamic material balance for this problem. So now finally that we have used our fundamental theorem of calculus, we can now rewrite these equations as dH1 over dt equals 1 over a multiplied by Qn plus Kc times E plus, now we can rewrite this integral as Ki times E minus Q1. And then our second equation, just to keep it simplified for this example, we now have dH2 over dt equals 1 over a Q1 minus Q2. And just as a reminder, we know that this Q2 here equals A out square root 2g h2 to the 1/2. So now we have our three equations and we have our dynamical material balance set up. So now for the next part, we're actually going to apply this into Colab and we're going to use Solve IVP to make some plots, because if you don't have plots, you don't get paid. So getting started, we are now going to apply this encoding to see a visual representation of what this proportional integral controller actually does. So to begin, I've imported all the libraries again. We have our NumPy, we have our scipy.integrate for our solve IVP, and we also have our subplot library from make subplots and plotly. So to start off first, we're going to identify all of our variables for this problem. And we're going to start off by identifying gravity, which is in meters per second squared, our area, or cross-sectional area of our tanks, which is 1 meter squared. We then have our cross-sectional area of our outlet tubes, which is 0.1 meters squared. And then once we have those, we can identify our Q and naught, which is also equal to 1 meters cubed per second. So then from there we can identify our initial height as well, and our initial height for this problem will come out to Q in naught divided by AH, and that all is squared. And then this will all be divided by 2 times our gravity. And then we'll set our set point for our heights, which for this problem we are just going to set as 20% higher times our h naught, because in the problem statement it tells us that the set point is 20% higher, and that's what we also applied in class. So we have our h set point, and then we can start getting into our controller gain. And to start off, we are just going to set this at 10 and label this controller gain. Now, we have our proportional integral controller, which we are going to label as Ki. And for this instance, we are just going to start out with a value of 0.1. And this we will just label as integral controller gain. So once we have that, we're also going to make it tell us our h naught and our h starting point. And if we run everything here, it provides us with the values of our initial height and as well as where our h set point is going to be at 0. Once we see our h naught and our h set points, what we're going to then get into is solving our initial value problem. And what we're going to start is we're going to simplify this left-hand side of the equation. So if I come back here on the iPad, we are going to simplify this equation, and we're going to label that as alpha. What this is going to enable us to do is make our coding a lot more easier and a lot more simpler to understand. So this will be labeled as AH times MP dot square root, and within the square root, it's just going to be 2 times G. And that is our alpha value for this problem. Now we're going to get into our IVP, and first we're going to define the right-hand side. And for this, like the previous problem, it's going to be t, comma, vector. And you can't forget a colon there, because you need to indent everything under this defining code in order for it to work properly. So once we have that, again, we're going to my apologies. We're going to set all of our heights as well as our EINT, which is our error. We are going to set this to vector values, because what this is going to allow us to do is it's going to allow us to see a constantly changing heights for both tanks as well as a constantly changing error value. So once we have our error, we can then move into defining Q1 and Q2. And this is going to come out to in our equation. It's going to be, and this is where things can get a lot simpler, is we do alpha and P dot square root of our height, just like in our equations that we wrote up. And then we will do the same thing for H2. All right, so we have our H values and our error. We have our H values, our Q values, and our error all defined for this problem. So next what we're able to do is we're able to set our error equation up, and that is going to be our HSP minus H2 for this problem. And once we have our error, then we will create our Qin equation, which we have written here. And then it's going to be Qin naught plus Kc times our E value plus Ki times our E integral value, because we use our fundamental theorem of calculus, which allows us to really simplify our integral for this problem, and we don't have to deal with it through Colab. And so now we also need to set a boundary that the E integral is separate from the E, and that they are not the same value. So once we have that, moving on, we can then use our return command to show us the values we need, and this will be our qn naught minus q1 value, bracket that, divide that all by the cross-sectional area, and then we will do the same thing for our second equation, which will be q1 minus q2, all divided by a, and then we also want to output the error. So once we have that, we'll hit run. It all ran correctly. We'll double run just to make sure. So we see that it returns the values that we need. So next, in the final part of this coding process, we will get into actually applying our make subplots from Plotly, and this will allow us to visually see where that proportional integral controller actually works when it has to fluctuate and work with the proportional only controller that we used in the previous part of this problem. Now for this final part, what we're actually going to do is before we get into creating our plot, we actually need to solve our IVP. So how we're going to do that is we're simply going to use the solve underscore IVP command that we got from our library above when we imported it. And that is going to be right hand side, which was our definition above with our t and our vector. This is going to be right hand side 0 to tendency, which we set as 1,000, I believe. If not, we will reset that above. And then we'll hit another comma, and this will be our h naught 0. And our method for this will be redow. And then finally, we will do another comma, comma, dense underscore output equals true. Once we have coded this for our solve IVP, we're going to then hit enter. And then we're going to apply H1 plot, H2 plot, and our E integrand is equal to res.sol tplot. So this allows us to solve our IVP, and then our tplot actually allows us to put this into graph format or a plot so we can get paid. And so how we're going to do this is we will do figure equals make underscore subplots. Then we're going to do fig dot add underscore scatter. And for our first graph, our x will be our t-plot, and this will be constant for both of them. Our y is going to be equal to h1 plot. The mode for this model is going to still remain as lines. And the name will equal as h1, just to identify our height plots. And we'll do the same here for h2. And then finally, because when we print this, it is going to be a really bright white color, and we don't really want that here, what we're going to do is fig.update underscore layout. And what this will allow us to do is really adjust the settings to what we need. So we'll adjust the height to 600, the height to 400, and then the template will equal I believe Plotly dark is correct. And so once we have all that, we have an invalid syntax here. And so when we look at this, we have Gemini explain the error for us. Oh, I do see the issue with this. So I don't know why Gemini's being like this. Please hold. So the only issue is we added a period where we should add a comma. So we're going to accept this change. And then we're going to run this again. Oh, and now we have tplot is not defined. So it looks like everything here ran correctly. So we're going to hit explain error here. So looking back through, we actually did miss because we didn't define it up here. We need to define our tplot, which is np.linespace, and this will be 0 to our from our tendency, and we'll assume 1,000 values for this problem. Now what we also need to call out here is our tendency, which we will set to 1,000. So now we run everything, and now we're able to get a graph. And our graph is just one straight line for right now. So the reason why we ended up having this straight line actually is because when we look back at my defined right hand side, what we did, I believe it was around here, we essentially had this q in naught equals q in naught plus these values. And so what the issue that came up with is it was not repeatedly making the calculations, and it was giving the same values for each set of calculations. So as you can see, what we have here now is we have our graph, and what we're going to adjust now is we're going to adjust this controller gain to 0.5. And as you can see, we start to get more and more oscillations as we increase the controller gain. So we're going to set the controller gain to 10 here. And as you can see, as we increase the controller gain, but we keep the integral controller gain the same, the oscillations become a lot more heavy, but in a closer time frame. So if we were to upscale our integral controller gain here, and we were to say make this 5, you would end up with a super unstable system and possibly explosions, or a lot of people would get hurt. So now if we reduce this back down and we set this to 0.1, say, and then 0.01 maybe, we get a very steady graph. So what we can see here is, really for all values of kc, there's some sort of value for ki, or so for all values of our controller gain, there's some sort of value for our integral controller gain we can use to make our system steady. And for this instance, we can see that by using a controller gain value of 0.1, we have a nice steady graph at the maximum of 0.01. Because if you were to make this 0.15, you do end up with, you eventually will get a steady system per this straight line here. But you notice just by upscaling it so ever slightly, you do end up unsteady at first, which could cause some issues, but then you will eventually reach a steady state. And now if we really crank this up, you see that we are in a very, very unsteady system in a very dangerous situation. So we have found where our integral controller gain and controller gain play a part in a system and the processes. So thank you guys for watching.